Today we continue with our study of calculus, differentiation specifically. We are going to look at some standard differential coefficients, and then we shall also look at higher derivatives. The following are standard differential coefficients. We have the function, we have the derivative. Number 1, s raised to power n, the derivative is s raised to power n minus 1. Number 2, the derivative of sin s is cos s. Number 3, the derivative of cos s is minus sin s. Number 4, the derivative of tan s is sec squared s. Number 5, the derivative of cosec s. Cosec s is the reciprocal of sin s, is minus cosec s cot s. The derivative of sec s is sec s tan s. Number 7, the derivative of cot s. Cot s is the reciprocal of tan s, is minus cosec squared s. Number 8, the derivative of the logarithm of s to base e is 1 all over s. And number 9, this is exponential function. The derivative of the exponential function e raised to power s is e raised to power s. But take note of something like this. If y is equal to e raised to power 2s, then the derivative of this one, you will now say let u be equal to 2s. So we now have, therefore, our du over dx is equal to 2. Then you now have y is equal to e raised to power u. And then you have your dy over du is equal to e raised to power u. So in conclusion, therefore, our dy over dx will be equal to dy du, which is e raised to power u, times du dx, which is equal to 2. And that will give you 2 times e, and your u is equal to 2s. Take note of that. We're looking at higher derivatives. Higher derivative is differentiation that involves repetition. We have first, second, third, etc. derivatives of a function. Let's take, for example, you are given y is equal to 3s raised to power 4. Then our dy over ds is equal to 12s raised to power 3. This is your first derivative. Your first derivative. If we differentiate again, it means that you are differentiating this function. We have d ds, so we now have d ds of d ds of this function 12s cubed. So that if you look at this one, it becomes d times d, which is d squared, of your 12s cubed, all over ds times ds is ds squared, which eventually means that you are differentiating this now, which is 36s squared. In other words, you have d squared of y all over ds squared will be equal to 36s squared. This is second derivative. Then we can also be told to find this d cube of y over ds cube is equal to, we had 36, which is 72s, And then you can go further and go on like that until there can be no more derivative of a function, or where the derivative becomes 0. We can even continue that way and see what we get. So we have d to the power 4 of y ds to the power 4, but this function becomes 72. So you can even go on now, d raised to the power 5 of y of ds to the power 5 is equal to 0, and that terminates it. Although at this level, we do not, in most cases, go further than the third derivative. So this one is your third derivative. This is your fourth derivative, and this is your fifth derivative. So you now know what we mean by higher derivatives. Let's take a look at some examples. Number 1. Find the derivative of y equal to sine squared s. Our solution, we have here y equal to sine squared s, which is the same thing as writing sine s all squared. Now we will let our u be equal to sine s because it's a function of a function. And so if we differentiate u with respect to s of sine s now becomes cos s. So we now have y equal to u all squared. We will again differentiate y with respect to u, and that will give us 2u. Now our dy all over ds will now be equal to dy all over du times du all over ds. Now substituting the values, we have 2u times du over ds is cos s. And this becomes, replacing u with your sine s, you have 2 of sine s, and then this is cos s. From trig identities, this is equal to sine 2s. And the solution is found. Example number 2. Find dy over ds, given that y is equal to cos 2s. The solution, we have here y equal to cos 2s. Now you can also let your u be equal to 2s, so that you differentiate u with respect to s to give you 2. Now you have y equal to cos u, so that you can differentiate your y with respect to u, and that will be minus sine u. And of course, we can now find our dy all over ds, which is equal to dy all over du times du all over ds. Substituting their values, we have minus sine u multiplying 2. So at the end we have minus 2 sine u, and your u is equal to 2s. That is the derivative of dy dx of the given function. Example number 3. If y equal to 3 cos s all over 3, find dy over ds when s is equal to 3 pi all over 2. Your solution, first and foremost, let us define what we mean by pi. We have pi radians. This is different from that arithmetic pi of 22 over 7. This pi radian is actually a measure in degrees, and it is equal to 180 degrees. So, when you now have 3 pi all over 2, you have 3 times 180 divided by 2, and that is equal to 270 degrees. So now, for us to find the y over dx of the given expression, we have our y. For example, let's start with y is equal to 3 cos s over 3 and close the bracket. As I said earlier, let u be equal to your s over 3. Then you differentiate u with respect to s, and that is equal to 1 all over 3. So you now have your y to be equal to 3 cos u. So you cannot differentiate your y with respect to u to be equal to. If you differentiate cos, you have minus sine. So minus 3 sine u becomes the derivative. Okay, now we are interested in finding our dy over dx, which means minus 3 sine u, and our u is s all over 3, and then times our du over dx, which is 1 all over 3. The 3 here, we cancel this 1 to give you minus sine s all over 3. Now we are told to evaluate this at the point where s is equal to 3 pi over 2, and we have calculated this to be equal to 270. So this will now be equal to minus sine 270 all over 3, which is minus, if you divide this, is 90 degrees. And then of course the value of sine 90 is 1, so we have minus 1 as the solution to the problem. And the answer is minus 1. dy over dx at the point s equal to 270 degrees is equal to minus 1. Example number 4. Find dy over dx if y is equal to sin s all over cos s. Solution. We have y equal to sin s all over cos s. If you observe this carefully, sin s over cos s from identity is equal to tan s. So our dy over dx is simply sec squared s, one of the standard derivatives. A student who is not able to identify this will go ahead to use the quotient rule. You will get the same solution, but you will have spent more time than necessary. And in most of these objective questions, especially in self-examinations at the JAM or UTME, which we are preparing you for, they may not have taken care of the time you will spend in using the quotient rule. They expect you to be able to have a knowledge of the identities, apply it, and then get a solution in less than 60 seconds. Example number 5. If y is equal to s sin s, find d squared y over dx squared. This means finding the second derivative of the given function y equal to s sin s. So the solution, you have your y equal to s sin x. You will now use the product rule. To solve this. In other words, this is your u and this is your v. So we'll take our dy all over ds is equal to your u, then find the derivative of the second one, the v over ds, plus your v, find the derivative, the u of the s. Now, your u, as you can have it there, is your s. The v over the s is the derivative of sin s. When you differentiate sin s, you have cos s. Plus, your v is sin s. Then you will now differentiate your u with respect to s. And your u is s. So if you differentiate that, you have 1. If you differentiate s, you have 1. Opening the brackets, this is s cos s plus sin s. That is the first derivative. For the second derivative, we have d squared y all over ds squared to be equal to, you will differentiate this and differentiate this. So if you differentiate this, you have s. If you differentiate cos s, you have minus sin s. Then of course, plus, you have cos s. If you differentiate s, you have 1. Plus, if you differentiate sin s, you have cos s. Opening the bracket, minus s sin s plus cos s plus cos s. Simplifying further, you have 2 cos s minus s sin s. And this is the second derivative of the given function. You can see that they are easy as long as you follow the principles, the rules guiding differentiation.